Foling will be telling us about more about monoidal structures.
Thanks, Hannah, and thanks everyone for coming back. Right, so in the previous talk, we introduced what are symmetric monoidal infinity categories and what are infinity operads. And we said that if we have an ordinary monoidal, symmetric monoidal category or an ordinary operad, we can do a construction via multi-category to obtain a symmetric monoidal infinity category and an infinity operad. Okay, so now in my second part, I'm going to first introduce more operads, the EN operads, and then I'm going to talk about algebras over operads. So I'm going to start with the one category concept. The little n disk operad, which are operating spaces. They consist of spaces, not just sets at each level. And these spaces are embeddings of little little n disks. So I have k numbers of unit disk in Rn, and I'm embedding it into another disk rectilinearly, meaning that it's all in the form of V sending to AV plus B for each of the embedding, and their image must be disjoint. So the space of all such embeddings is the space Dn of K. Like what I draw here is an element that belongs to D2 of 3. And the composition or the structure maps, which I draw here, being D2 of 2. So the 2 is the 2 disks here, cross D2 of 2, cross D2 of, let me add 1, 3 to D2 of 5, which is 2 plus 3, comes from composing these embeddings. This gives me an operad, and this operad has been used to recognize n-fold loop spaces. So the story is as follows. Dn algebras, which we also can call them as En algebra, sort of, let me go, wait, what do I want to say? I want to say that n-fold loop spaces are Dn algebras, and Dn algebras can be delooped. So there are also n-fold loop spaces up to group completion. So the story is as follows. If I have an n-fold loop space, then here I want to do, say, with this, I want to do D2 3 cross loop 2 of y to the 3 times and landing loop 2 of y. I'm claiming loop 2 of y is a D2 algebra, then I need to give these kind of maps. Okay, what is this map? Here I have 3 maps, 3 elements in loop 2 of y, so there are maps from S2 to y. And I can think of them as D2 quotient the boundary of D2. Wait, where did my pen go? I cannot write. Well, I'll just okay, I'll just say it. So mapping everything in the image of the disk using this map fi, and then mapping everything outside the image to the base point. So I will get a map from the big disk to y which is identity on the boundary. So that's an element in loop 2 of Y. Okay. I'm going to.
Are you trying to reshare?
Yeah.
Yeah, I hope it can fix the problem.
Is it because of the pen? Yeah. Okay. Oh, I have a different version with everything. Hope. Okay, cool. All right. Since I can write, I'll just use this version. Okay, so we said that if X is n-fold loop of Y, then X is an Dn algebra. And on the contrary, if X is an Dn algebra, then there exists an n-fold loop space, loop n of Y, and a map from X to loop n of Y, which is a map of Dn algebra such that this map is a group completion in some sense. So the upshot here is that combining these two directions, we get group-like Dn algebras are equivalent. The category of it is equivalent to the category of n-fold loop spaces. And if we let n goes to infinity, group-like E-infinity algebras are equivalent to infinite loop spaces, which are equivalent further to connective spectra. Right, so that's the role the little n this opera has served in the history of algebraic topology. And we can understand these n-fold loop spaces in comparison to algebra. If we take pi 0 of n-fold loop spaces, we will get pi n of the space. So if n is 0, E0 algebra, zero-fold loop spaces are E0 algebras, and they are just base spaces. And pi 0 of it is just a set. And when you increase n, you have more and more structure on both sides. On the left, you have E1 algebra, E2 algebra, and so on until E-infinity algebra structure. But on the right, you have group structure on pi 1, and then you jump immediately to a billion group structure starting from pi 2. So in algebra, you do not see this hierarchy of coherence from 2 to infinity. You just see a single jump there. So that's why sometimes homotopy theory are used to study algebraic questions, because here we have more structures that's visible. Okay, so from that operad, I want to build an infinity operad. And before, we just said if we have an operad in set, then we can do the multi-category stuff, and then we can build that infinity operad. Here I have an operad in spaces. So what should I do? Well, I first turn spaces into simplicial spaces. So now my O, which was my little disk operad, for example, is a simplicial operad. And it's furthermore fibrant, meaning that all simplicial sets, OM, are fibrant simplicial sets, or equivalently complexes, because they come from spaces, so they are fibrant. Okay, and now my old tensor constructed as before is not going to be a single category, but it is going to be a simplicial category. So it's mapping things are not just mapping sets, but mapping simplicial spaces, and they are all fibrant simplicial sets. So it's a fibrant simplicial category. And then you can take the simplicial nerve of this fibrant simplicial category, you will get an infinity category. And that gives us an infinity operad. And we define this to be the operatic nerve of O in tensor of O. that's how the EN tensor is constructed. All right. Okay, so now I'm going to talk about algebras over an operad in the infinity category setting. The task here is to define O tensor algebra in a symmetric monoidal infinity category C tensor. And we are going to do this in a more general setting. So we are going to start with two infinity operads, P and Q. So C tensor being a symmetric monoidal infinity category is a special case of an infinity operad. And for an infinity operad, we define inert morphisms to be those morphisms that are both P co-Cartesian and they map to inert morphisms in thin star. So, and we have seen examples of inert morphisms in O tensor when O is an ordinary operad. We see that the unit in O1 is inert. And in C tensor, when C is a symmetric monoidal category, we see that the row i's, which pick out coordinates, are inert. So inert morphisms basically are forgetful functors, and they should be preserved when you think about map of infinity operads. So that's the definition here. If you have a map over thin star, nerve of thin star from O tensor to C tensor, meaning number one commutes here, then F is a map of infinity operads if it satisfies number two, which says that it sends inert morphisms in O tensor to inert morphisms in C tensor. And being inert, let's recall the definition, says that its image in thin star is inert and it's P co-Cartesian. And where its image is doesn't change if your map is over nerve of thin star. So F, number two basically says that F sends P co-Cartesian to Q co-Cartesian if your co-Cartesian is over an inert morphism. Okay. And number two can be satisfied if F preserves just inert morphisms over the kind of row i's. Row I is a special case of inert morphism, and going to delete this. That's the reason. That's the argument. If F preserves inert morphisms over row I, then it will preserve inert morphisms in general. Right, and then we write alg O of C for the full subcategory spanned by infinity operand maps. And if O tensor is the commutativity operad, which is the identity map from nerve of thin star to nerve of thin star, then alg O of C is written as commutative algebra in C. Right. And now I'm going to generalize from symmetric monoidal infinity category to O monoidal infinity category. So when we talked about algebra object, we are looking at maps from O tensor to C tensor. And now I'm going to do the opposite. I'm going to consider C tensor to O tensor. This is a proposition, and you can check the proof in higher algebra 2.1.2.12. It says that if I have an infinity operad O tensor and a co-Cartesian fibration C tensor over O tensor, then the following are equal. Number one, the composition is an infinity operad. Number two, for all P in O tensor over N, an object in O tensor, and the P co-Cartesian lifts of it. P co-Cartesian lifts starting at T of row I from N to 1. So Ti is an object in O tensor of 1. Okay, row I bar induces an equivalence of infinite categories of C over the fiber of T to C over the fiber of Ti multiplied together. Let me think. Okay, so I paused a little bit to read this condition number 2 more carefully, and I hope you also use the time that way. The number 2, t sits on n and ti sits on 1. So number 2 is actually very similar to the Siegel condition, but just we are using O tensor instead of thin star. So this is the adaptation of the Siegel condition to over O tensor. Right, and the proposition says that these two things are equivalent. When this is satisfied, we say P is a co-Cartesian fibration of infinity operads. So we have an infinity operad C over thin star, we have an infinity operad O tensor over thin star, and we have a map which is a co-Cartesian fibration. And we also say in this case that P exhibits C tensor as an O monoidal infinity category. And it's not explicit, but actually, if this is satisfied, then number 1 or 2 is satisfied, then P is automatically a map of infinity operads. So in summary, O monoidal infinity category is a co-Cartesian fibration of C tensor over O tensor, where both of these are implicitly over nerve of thin star, so and being infinity operads. So example, if we replace O by com tensor, which is the identity map from nerve of thin star to thin star, then O monoidal category, which are co-Cartesian fibrations of infinity operads, C tensor to com tensor, are just the same thing to symmetric monoidal infinity categories. So we are changing the role of nerve of thin star to O tensor in this definition. And we do have this requirement in the definition of a symmetric monoidal infinity category.
Okay, can I ask a question about the proposition you just proved? It's like, can I understand the condition 1 as saying like the composite has a Siegel condition, and then the condition 2 says like I'm for some reason I can't see the condition, but is that like condition 1 is the composite has Siegel condition, and then condition 2 is like the first part of it has Siegel condition. Is that something like that?
Condition 1 says more than Siegel condition. So an infinity operad has 1, 2, 3. 1 is the relaxation of co-Cartesian fibration, and number 3 is the Siegel condition. But there's also number 2, and also like we have this.
Okay. Yeah, I was thinking. Oh, right. Okay, so it's more subtle than that. Okay.
Yeah, but they are equivalent. So in the end, it has the Siegel condition.
Yeah, they did assume C2O is a co-Cartesian fibration, so maybe that's something. Thanks.
Yeah. Yep. Okay, so now this is a notion called co-Cartesian fibration between infinity operads. And next is a notion of fibration between infinity operads. Okay, a map of infinity operads is called a fibration of infinity operads if it is a categorical fibration. And this means fibrations in the Joyal model structure. And you can take this as a black box. And if I already have a map of operads, which is an inner fibration, then the following are equivalent, which says number 1 is a fibration. Number 2, I start with objects X here, C here, and inert morphisms below. So fixing the source, I can lift the inner morphism to inner morphism in O tensor. So that's condition 2. And if either of them is satisfied, then inert morphisms in O tensor are exactly those morphisms being both P co-Cartesian and PE being inert in C tensor. So on the left, inert is defined over N of thin star. And that it's saying it's O tensor over thin star co-Cartesian and PE being inert. But on the right, it's P co-Cartesian. And these two things are in general different. But here I'm saying if it's a fibration, then these inert morphisms are exactly those that are just P co-Cartesian and PE being inert. And an example is that if I have an infinity operad, viewing this as a map of infinity operads from O tensor to com star, this is a fibration of the infinity operads. And note that this is not a co-Cartesian fibration because this P may not be a co-Cartesian fibration. That's requiring it to be a symmetric monoidal infinity category, but I'm just starting with an infinity operad. Okay, and fibrations of infinity operads are relevant when you want to look at algebras over O. So if you want to look at algebras in C tensor over O tensor, you had better have C tensor to be a fibration of infinity operads over O. This is a definition. If you have a diagram like this, an infinity operad map and a fibration, then your algebras in C tensor under O prime above O are defined to be the infinity category of just map of infinity operads fitting into this diagram. And when O prime equals to O, we write it just as algebra over O. And this should be the correct notion of O algebra in an O monoidal category. Because if you think about O prime and O being nerve of thin star, then such a map F, what's below is automatic, and such a map F is just a map of infinity operads. So when they are both nerve of thin star, this is just commutative algebras in C. Right, and now we want to generalize commutative algebras in a symmetric monoidal category to O algebras in an O monoidal category. So we had better have O both into it and of above and below. Okay, and this is a summary of how to understand these notions. Co-Cartesian fibration of infinity operads is stronger than fibrations of infinity operads and stronger than map of operads. How do we see this arrow? We can see it. Let me think. Well, we can see it in different ways. One way, which is a little bit cheating, is to just look at this definition. If I am a categorical fibration, if I'm co-Cartesian fibration, then I'm automatically a categorical fibration, but not the other way. And you can also see it by checking the definition using these lifts and this criteria of inner morphisms. But anyway, we have this implication, and it's more convincing if you consider if you think of this as C tensor over O tensor and you fix O tensor to be com tensor, then co-Cartesian fibrations over O com tensor or N of thin star is exactly symmetric monoidal infinity category, and fibration over infinity operads are over com tensor are exactly infinity operad. Okay, so this is how we think about these notions. Okay, and these are things I'm going to talk about. And then there should be things below. Wait, what happened? My computer is pretty old and but the memory is fine.
Maybe you can try the other document.
Yeah, I want, but I'm going to restart OneNote. Okay, now I have it.
Great. You're not. Oh, okay. You just started sharing.
Yes. Yes. Okay, so now I'm using a reference from a paper by Gross called what's called? Hannah shared it
a
few days ago, and
a short course on infinity categories, I think.
Yeah, a short course. Yeah, thanks. Right. So I'm going to use the definition there and compare it to the definition in higher algebra. So here we have two symmetric monoidal categories P and Q, and a functor over nerve of thin star is called symmetric monoidal if it sends P co-Cartesian edges to Q co-Cartesian edges. It's denoted functor tensor M tensor to N tensor. And it's lax symmetric monoidal if it sends inert edges to inert edges. So number one is stronger than number two because inert means P co-Cartesian end over inert edges. So there are fewer of them than these. And if you think about this definition, then and compare it, then number two is the same as the definition of commutative algebra objects in N. So by commutative algebra objects in N, we actually mean lax symmetric monoidal functors from nerve of thin star to the symmetric monoidal category N tensor. Okay, and now I'm going to remove the symmetry I'm going to do monoidal categories. I will first start with a less common route, but a more natural route if we are in this talk, which is before when we did symmetric monoidal categories, we look at the commutativity operad, and then we looked at com tensor, which is nerve of thin star over nerve of thin star, and then we look at co-Cartesian vibrations over that. Right, and now we want to look at monoidal categories, which should be, if you think about commutative monoids and monoids, then this should be parameterized by the associativity operad. So we replace nerve of thin star by the associativity tensor. And we make this definition that a monoidal infinity category is a co-Cartesian vibration of infinity operads over associativity tensor. Okay, and a proposition in higher algebra tells us that if you have a map of infinity, if you have an infinity operad and you want to tell when is it a symmetric monoidal infinity category, then you just need to check that its pullback to a associativity tensor is a monoidal infinity category. Okay, and now I can talk about algebra in C, with C being an infinity operad with a fibration to a associative tensor. So these are, we said that we want to look at algebra over an operad, had better have that to be the category to start as a fibration over it. And another more common definition of a monoidal category is the following, and I'll call it A infinity monoidal, just to distinguish with the notion before. It's also the notion in higher algebra. An A infinity monoidal infinity category is a co-Cartesian fibration over the nerve of delta op, such that the Siegel maps are equivalences. And this looks very similar to the definition of symmetric monoidal infinity category. You have the co-Cartesian condition and the Siegel condition. But it's not, well, it just looks the same, and it's not a special case because nerve of delta op is not an infinity operad. This is the answer to one of the homework questions. Yeah, here I have a, so now I want to study the category delta op and thin star. And I have a remark saying that the maps rho I, which gives the Siegel maps, are in the image of the inclusion of delta op to thin star. And we call morphism in delta op, k to n in delta op, or n to k in delta, we call it convex, or just call it inert, if it is injective and its image is an interval, alpha of 0 to alpha of n. So if we sit down and think about what is this functor, this condition being convex is exactly saying that its image is inert. Okay, I can leave this as a homework problem too. All right, and now from an A infinity monoidal category, we define algebra objects in it as a section such that convex morphisms are sent to P co-Cartesian morphisms. And we have seen flavor of this before. Basically, we have n here, m tensor here sitting over n delta op, and n delta op mapping into it, so it's a sort of a map of infinity operads if they had been operads, and it sends inert things to P co-Cartesian morphisms, which automatically are inert. So this is the definition of an algebra object. And we can also talk about lax monoidal functors and monoidal functors. If we have two A infinity monoidal infinity categories, then if P sends P co-Cartesian edge to of convex morphisms, meaning inert morphisms, to inert morphisms, then it's lax monoidal. And if we preserves all co-Cartesian morphisms, then it's monoidal. And the definition, A infinity algebra, or this associative algebra, I mean A infinity algebra, is the same as the definition in number 1. It's the lax monoidal functors from nerve of delta op to M tensor. Okay, so up until now, we are having a very similar flavor to the story of infinity operads, with the distinction here, as a remark here, that P as this is not an infinity operad, but it is some generalized version called planar infinity operad. And there is a comparison of these two definitions. The map from n delta to fin star actually factors through associativity tensor. So to see this, you need to think about what this actually is and what this map actually is. So delta op mapping to fin star objects, it all works. On morphisms, its image will be like a sequence of things sending to 1, a sequence of things sending to 2, a sequence of things sending to 3, and so on. And then you have the remaining things sending to 0. And associative tensor, the morphisms there are maps in fin star plus a linear ordering in each pre-image. And since your morphisms here come from, well, you don't have to come from delta n. You have natural ordering on the objects here as well. You just pick that natural ordering. Then the image here factors through this map. So there is this inclusion called cut. And in fact, if you take cut or nerf of delta op to associative tensor, which I mean nerf of this, this map is sort of an approximation to the infinity operad associative tensor. In the sense, actually, I don't understand. So I listed it here just to convince you that these two, one being an infinity operad, the other not being an infinity operad, are closely related. And we have the following proposition which says that if you have a fibration of infinity operads, then composing with this cut map will induce an equivalence of infinite categories of algebras in O and A infinity algebras in O, where the left is defined using this, and the right is defined using sections of this category. Okay, so the upshot of this part is that by generalizing symmetric monoidal to O monoidal and taking O equal to associative tensor, we can define monoidal categories. And then there's a different definition using the nerf of delta op, and these two definitions agree. So that's the upshot. Okay, and now the next part is about modules, and it's going to be without any proof. So again, we start with a fibration of infinity operads. And if you don't like this notion, you can just think about the special case when this is nerf of fin star. So you have just one infinity operad C tensor over nerf of fin star. And then you will get an infinity category of algebra, O algebra objects in C. And if you fix an O algebra object in it called A, and with some assumption on O, which is it's unidal, which is about saying that if you had come from an ordinary operad, then the zero space is contractible. Then you will get an infinity category of A module object in C. A classical version of the story is that if you have a ring, then you have the module over the ring. So this is generalizing that. And if we have that O is some coherent infinity operad, with examples, all our operads are coherent, and its definitions I'm not going to include, then you actually can extend this infinity category to be the fiber over 1 for some tensor, and you get a fibration of infinity operads over O tensor. And in some good cases, this P is going to be a co-Cartesian fibration of infinity operads. Okay, what does this say? if you take O to be nerve of thin star or com tensor, this is saying A algebra, if A is a commutative algebra, then A algebra or A module objects has a symmetric monoidal structure. If in this case. Okay. And the next part concerns limit and colimit. I think I'm going to skip this part. Basically, it's studying when does the forgetful functor from A module object in C to C preserves limits and preserves colimits. And the answer is that it always preserves limits. And if the tensor product commutes with colimits, then the forgetful functor preserves colimit. Okay, so that's the it's not very detailed anyway, so I'm going to skip it. Maybe I shouldn't. Sorry about this. Okay. Okay, so the last part of the talk is studying EN algebras in spectra, and these guys are called structured ring spectra. There is a map of operads, infinity operads from E0 tensor to E1 tensor up until E infinity tensor, which is equivalent to commutative tensor. If you think about little disks, what this map is doing is if you have embedding of n disk into n disk, then you can think about embeddings of n+1 disk to n+1 disk aligning on the equator. So in the last coordinate, you just always map to 0, then you will get a map of operads. And in terms of algebras, this is saying that algebras of this operad forgets to algebras of the previous operad up until algebras over E0 tensor. And if I have an E1 spectrum R, then I can define left module over R in spectra. And I will drop the spectra in the notation. I can also define right module. And this is defined using means of multi-categories, which I'm not going to explain. Then if furthermore my R is E infinity, meaning it's a commutative algebra or commutative ring spectrum, then left module over A is equivalent to E infinity module over A, E infinity A module. And this left module category, first of all, it's a stable infinity category. And if the E1 ring R, E1 ring spectrum R is connective, then the module category also inherits an accessible T structure, and the pi 0 gives an equivalence from the heart of the T structure to nerve of the pi 0 R modules. This is basically saying you have less or equal to n and greater or equal to n parts of this category, and the equal to 0 part, the heart of that T structure, is just the category of pi 0 R modules. And if R is discrete, meaning it's a classical associative ring, and you think of it as a ring spectrum by, for example, by looking at the element MacLane spectrum of R, then more can be said. So first, we can form the abelian category of left R module called A. And then the heart of the spectrum left R module is equivalent to nerf of this abelian category, which is the heart of the bounded derived category of A. Well, I'm not planning to do these details, and these you can ignore all this. From this, the upshot is that you can obtain a map from the derived category of A to left R module, and this is an equivalence. The derived category constructed using classical means is equivalent to this spectrum category. And if my R is not just a E1 ring, but it is actually it's not just an associative ring, but it's a commutative ring, then that equivalence can be upgraded to a symmetric monoidal equivalence of infinity categories, dA to mod R, where the left side is has symmetric monoidal structure coming from the tensor product of chain complexes. Okay, and these are some results I'm presenting, but I don't want to go into the proof of those. But there's one element in the proof that I want to mention, which is the recognition principle. And this is interesting to know in its own right. Let's start with the E1 case. It's a theorem by Schrader and Shipley. It says that if you have a stable infinity category, how do you know when is it a module category for some E1 ring? And these are E1 ring spectrums, so I didn't write the spectrum. And the right is the right module category and left module category are equivalent. And it is the module category for some E1 ring spectrum R if and only if this stable infinity category is presentable and that there exists a compact object in it, which generates C in the sense that if X from C to D is 0 for all n, for an object D, then D is the 0 object. So these are all some categorical characterization of your category C. And the theorem says that if you have these properties, which are satisfied for a module category, then you are a module category. And in fact, you can take R, this E1 ring R, to be the endomorphism of this object C. And endomorphism is automatically an E1 algebra. And if you have an EN algebra, if you have an EN monoidal category, then the endomorphism of the unit is EN plus 1. And that's used in the next theorem, which generalizes the previous one to higher K. Now K can be from 1 to infinity. And the functor that sends R to right modules over R, when K is infinity, these are just R modules without right. This determines a fully faithful embedding from EK algebras to EK-1 monoidal categories. And more precisely, these are EK-1 monoidal presentable infinity categories. So these are EK-1 algebras in PRL. And then, something is in the image, that's the recognition part. Its essential image consists of those functors of those EK-1 monoidal categories, so that first, the fiber over 1, C means the fiber of C tensor over the object 1. It's stable and presentable, and we also requires the tensor to preserve small co-limit in each variable if K is greater than 1. Tensor is not explicit, but if you have K greater than 1, which means K-1 greater than 0, so it's at least E1, then an at least one monoidal category will come with a tensor product, and we want that tensor product to preserve small co-limit in each variable. And number 2, the unit object is asked to be compact, and number 3, the unit object generates C in the same sense as above. If these are all true, then this is in the essential image, meaning you can find an EK algebra R in ring spectrum such that its module category is equivalent to this EK-1 monoidal presentable infinity category that you start with. Okay, that's end of my talk today.
Okay, let's thank Foling for the